Most people want a clean, fair, and sustainable world, and it is frustrating that's not happening sooner. Political indifference or vested interests do contribute to this, but there's also a host of technical problems that have to be solved before we can reach this green future. We can't overhaul the entire world without overcoming some obstacles along the way. My name is Cormac O'Malley. I'm an electrical engineering PhD student with a research focus on low carbon power system operation. And I want to delve into these problems with you and hear from experts about the solutions that research can offer.
From the Integrated Development of Low Carbon Energy Systems programme at Imperial College London, this is Low Carbon Conversations, a podcast on the challenges of building a decarbonised energy system and the research that's helping us to overcome them. This podcast is supported by Energy Futures Lab, Imperial's Energy Institute. For more information, visit imperial.ac.uk/Energy Futures Lab.
In this episode, what happens when things go wrong on the electricity grid? Operating our power system is a delicate balancing act. Electricity generation and demand need to be equally matched around the clock. But how do we keep electricity flowing when a power station fails? And how will that balancing act change as we move towards a greener future powered by renewable generation? My guest today is Dr Luis Badesa Bernardo. His research looks at methods to integrate renewables into electricity grids in a cost-effective and secure manner. Luis holds a master's degree from the University of Maine and a PhD in electrical engineering from Imperial College London. He's also worked as an energy consultant outside of academia and is the perfect guest to explore this obstacle with. I began our conversation by asking Luis how he'd summarise his work and what is required to keep a system running after the sudden loss of a generator.
Most of my work, as you said, is related to keeping the lights on, as we would say, when any of the generators in the system is lost. So what that means is that we need to always keep the balance between demand and generation, but sometimes, for whatever reason, some of the generators that is producing energy at a given time has to go offline because there is a fault caused by a lightning strike or any cause that you might think of. Then there is an imbalance between demand and generation. So that's what we refer to as a loss of generation. And that imbalance has to be compensated if we want to keep the lights on. So that's basically what I study in my research.
So the problem is a generator might just trip off the system for whatever reason, and then we're left with less generation capacity, but our demand stays the same because people don't just suddenly turn off their lights when, a generator trips off the system. And so we have less generation, the same demand, so therefore there's an imbalance there.
Why is that a bad thing? And, what happens if there's an extended imbalance?
What happens is that the frequency of the electricity grid will drop to levels that are simply not acceptable. So electricity grids there are AC currents and voltages there, therefore there is a frequency. And that frequency must always be close to 50 hertz. It cannot go well below 50 hertz because there are some protection devices in the system that would disconnect load to always keep some balance. So as I said, if we lose a generator, we have more demand than generation.
So presumably on the system, we've always needed to keep this balance between generation and demand. Why is it something that warrants looking at now? And is it at all related to us going into a decarbonised future?
It is, yes. So we have always needed to keep the balance between generation and demand. However, the challenge is increased when we have more renewables. And the key word to explain this increased challenge is inertia.
Oh.
So explaining inertia in very simple terms is just a rotating mass. It's the rotating mass that we have in typical power generators like nuclear units, like gas-fired power plants, like coal power plants. They are no longer generating a lot in the UK, but they are in some other countries. So these generators have a rotating mass, and that mass stores kinetic energy as it rotates. So when we have the loss of any generator, that energy stored in the inertia was spontaneously released into the system. So basically, we still needed to eventually either increase generation or decrease demand to compensate the loss of a given unit. However, that kinetic energy stored gave us time to contain that imbalance because we could spontaneously use that energy.
So you could look at this inertia as some sort of buffer, or sort of buys you time.
Yes, definitely. It's a buffer, an energy buffer, and it's exactly as you said, it buys us time when there is a generation loss.
You talk about inertia as an immediate release of energy into the system as a way of compensating the sudden energy deficit that comes after a generation loss. And it comes from this slowing down of the spinning turbines in fossil fuel plants. So this slowing down, does that have something to do with the dropping frequency you were talking about earlier?
Yes, definitely. So the speed at which these masses rotate, that's exactly what sets the electric frequency of the grid at 50 hertz. So in normal conditions, they would be rotating at an equivalent speed to 50 hertz. However, when they release this energy, they start to slow down. And that's what we see in the grid. So the frequency of the voltages starts to decrease. And that's a consequence of this physical slowing down of the synchronous masses of thermal plants. So then one could ask, okay, but then why do we really look at frequency? Why is that important, right? Why do we have to keep it within 50 hertz? And I could give you a simple comparison. It's like when you go to the doctor and the doctor maybe checks your heart rate. So if he sees that the heart rate is above or below the normal values, then he might do further tests because there might be something wrong with your heart, right? So it's a similar concept with the grid. When we look at the electric frequency, it's not that we care about the frequency so much, but it's telling us that there's a generation demand imbalance there. And that's what we care about, because that could lead to a blackout. That's what we need to keep the frequency within a very narrow band around the nominal 50 hertz.
Okay, and you say that it comes from the rotating mass of thermal plants. So wind turbines have quite a big rotating mass, especially if they're rotating quite fast. Can they offer this inertia service?
Not directly. They can offer something called synthetic inertia. And the reason why they cannot offer pure inertia, what we call synchronous inertia, is because they are decoupled from the grid through power electronics converters. So in the case of a gas-fired power plant, we can control the flow of gas into the turbine and make sure that it always rotates at 50 hertz, which is the frequency of the electricity grid. However, we cannot control wind speed. And to maximize the energy that we extract from the wind, the turbines rotate, the wind turbines rotate at different speeds, not always synchronous speed. That's why we need the power electronics converter there, because eventually the power that is injected into the grid must be at 50 hertz. And that's what the power electronics does. So yeah, just to summarize, that power electronics device decouples the wind turbine from the grid. And that's why it doesn't spontaneously release the energy stored in any mass.
So power system inertia is really the crux of our conversation we're having here. The physical definition of inertia is a resistance to change in velocity, but in power systems you can think of it as a resistance to change in frequency caused by a demand generation unbalance. This is determined by how many synchronous thermal generators you have on the system, because it is a property intrinsic to the rotating mass of these turbines. Fossil fuel plants are synchronous because they rotate 50 times a second to produce electricity at 50 hertz. Renewables are not synchronous, so do not increase system inertia, which means that the frequency of a system with a lot of them on is harder to keep within secure limits. And this is important to do because otherwise we risk damaging the system or blackouts.
You say that this having a lot of inertia or thermal plants on the system buys us time after a loss of generation. But what is it buying us time to do? If it doesn't solve it in itself, what other tools do we have to to correct this unbalance after a loss of generation?
Sure, that's a great question. So we have a service called frequency response, but it's actually very simple to understand. It's just a power injection that comes after the loss of a generator. So for example, let's say that we have 10 units generating at a given time in the UK, let's say, and we lose one of them. Eventually, the remaining 9 units could increase their power output to compensate for the lost generator. That's what we call frequency response.
And that's different from inertia because they are, are you putting in more fuel and you're burning, so you're burning more energy, and so you're effectively increasing the energy input and not just extracting this kinetic energy from the rotating turbine.
Yes, that's exactly what happens. So inertia is something that doesn't even need to be controlled. You just have the rotating mass connected to the grid, and whenever there's a generation loss, the buffer simply releases that energy. However, frequency response needs a control mechanism. And just like you said, we need to burn more fuel to increase the power output.
So with this lowering of inertia caused by more renewables coming onto the grid and fewer thermal plants, would it be fair to say that we need more of this frequency response? And how much more do we need?
Well, that's the million-dollar question. Actually, my whole research deals with that question in a sense. So in simple terms, yes, we typically need more frequency response because we need to control the frequency nadir, the lowest point that the frequency in the electricity grid reaches after generation outage. However, if we can obtain very fast frequency response, the volumes that we need of frequency response overall won't be significantly increased, even if we have a lot of renewables, and that decreases the system inertia. So that's another key for frequency response, is how fast can we get this power injection into the system? Because generators are somehow slow machines. However, we have newer devices connected to the grid, such as battery storage, which have much faster dynamics. And they could provide something in the UK is called enhanced frequency response. In other countries, simply fast frequency response. And that could be one of the keys to solving the low inertia problem in grids with a lot of renewables.
So you say we need more frequency response in the future to deal with the lower inertia. Where are we going to get this frequency response from, and what's it going to cost the electricity user? Is it going to end up costing us more money than we're saving by using the cheaper renewables?
Again, that's a great question and with a very difficult answer, but probably not. It's not going to cost us more than right now, because what I mean is energy costs are going to drop because we don't need to burn fuel to produce electricity from wind or from the sun through PVs. However, it is true that the cost of these ancillary services, as we call them, this inertia and response, are going to increase. The key is, as you said, there is a cost related to these services. We can think of them as insurance in a sense. So they are there just in case we lose a generator, so in case there's a fault in the system, and they are there to keep the lights on. But we need to pay for them. Let me just give one example. The typical providers of a frequency response have traditionally been part-loaded generators. What I mean by that is that generators that are not operating at their maximum power output could eventually provide a power injection into the system, but they need to be operating at a lower than maximum output. That means that they lose efficiency, so they need to burn a little more fuel to produce the same amount of electricity. So there's an implicit cost there. That's where the insurance cost comes from.
Kind of like an opportunity cost.
Yes, definitely. So that's why we don't procure huge amounts of these services, because there is a cost related to them. And there is a market in the UK. So generators get paid for this service.
Okay, so I think I have a good idea of the problem. Just in terms of the scale of the problem, is it likely that this lowering of inertia is something that we can solve, or is it something that has a serious chance of holding back the energy transition because solving it costs too much money and makes higher and higher penetration of renewables infeasible?
Definitely, it's a challenge, but we can solve it because we know how to do it. It's just the current tools that we have would be more expensive than we would like to. It's a matter of putting in place the right incentives in the market for new technologies to provide these services, and also to unlock flexibility from new devices that will come into the grid. So let me just give you two examples. In 2019, there was a new product created in the UK, a new frequency response product called Enhanced Frequency Response. And the requirement for this product was that the speed of delivery of this power injection had to be much faster than previously. Therefore, the auction that was held in 2016 was won solely by battery storage. So battery storage, as I mentioned before, can provide really fast power injections. So that's an example of how to create market incentives for new providers. If battery storage is going to have to compete with conventional generators, although they can be much faster in delivering frequency response, probably we're not putting in place the right incentives. However, if there is a separate market that really recognizes this faster speed, that's how we can get people and investors interested in this service.
Because they're rewarded more highly for a sort of more effective service.
Yes. Well, all these things are complicated. In reality, the prices in 2016 for this enhanced frequency response product were not very high, but at least it was a starting point. And battery storage had the way there of getting into this market. But yeah, and another example of what I meant by unlocking flexibility. You can think of EVs, which are going to become much more common in the future as we need to decarbonize our transport.
Just to clarify for our listeners, EV stands for electric vehicle.
EVs are essentially a battery. So by appropriately operating EVs, and by that I mean putting in place incentives in the market for EV owners to plug their EVs at certain times, we could unlock a lot of flexibility from these distributed devices. And unlocking flexibility basically means increasing liquidity, and very liquid markets have the consequence typically of a drop in prices. So eventually we could get these services for not a very high cost. It's just a matter of understanding how we need to change our operational practices to become cost effective.
Oh, okay. So if I'm understanding you correctly, you're saying that distributed providers like EVs could actually provide this service just by lowering their demand or injecting more power into the grid. Is that correct?
Yes, that is correct. There is, however, an additional challenge with distributed providers, and it's the fact that they cannot. There are many different units. We can think of even millions of EVs in the future, which makes it much more difficult to coordinate them and to control them, because basically the owner of each EV is the person who eventually makes the decision of providing a certain service or not. It's easier if we just have a few generators in the system, or maybe a few grid-scale battery storage projects, because it's easier to communicate with them, to control them in a somehow centralized manner. So in summary, it's an additional challenge to procure these services from distributed providers, but it's certainly possible. There's still active areas of research in that topic, however.
Two bonus questions I'm going to ask you. If you could click your fingers and a machine appears with any characteristics you like, what do you think the machine that would most speed up the advancement of decarbonization would be?
I think nuclear fusion, probably, in the sense that it would be a controllable generator, which is something that wind or solar are not. At the same time, it would be zero carbon, which is what we're aiming for. And I guess it would be a synchronous generator, therefore it would provide this inertia that we will be lacking in systems really dominated by renewables. So that would be probably the one technology solves all, or probably not all, but most of our problems.
Global warming destroys ecosystems and threatens mass extinctions. If you could click your fingers and de-extinct any animal that is now extinct, which one would you pick?
Wow, the first one that comes to mind is the dodo, right? I don't know why, it's just looks funny.
That's a good enough reason as any, I guess. Thank you so much, Luis.
Thanks for having me.
Thanks for listening to Low Carbon Conversations, a podcast from the IDLES programme at Imperial College London. If you'd like to get in touch, email us at idles@imperial.ac.uk. For more information about energy research at the college, or to learn about our internationally unique Master's programme in Sustainable Energy Futures, visit imperial.ac.uk/Energy Futures Lab.